So this is chapter 3, section 3 of calc. And we're just trying to apply the derivative. It's just really more of the same stuff, I feel like, what we've always done. Just using the derivative and thinking about different ways you can use the derivative. So here, find the open intervals on which f of x equals x cubed minus 3 over 2x squared is increasing or decreasing. So when you're trying to think about when stuff is increasing or decreasing, well, think about what it means when it's increasing or decreasing. So if it's increasing, it looks like that, right? Because that's one thing. Remember, you're always looking left to right on these graphs. So if it's increasing, it looks something like that. If it's decreasing, it looks something like that. And so you think about the slopes, or you think about the derivative, which is the slope. Well, here, when it's increasing, the derivative is positive, right? This is the derivative, slope of the tangent line. When it's positive, that's when it's increasing. When it's negative, that's when it's decreasing because it's going down. The slope of the tangent line is negative. So when we're talking about increasing or decreasing, that's what we're thinking about, is when is the derivative positive, when is the derivative negative. So we're going to start out to find that by taking the derivative. So if we take the derivative, f prime of x is 3x squared minus 3x. So what are we going to do? Well, how do you determine, this is an inequality, right? We really just want to know, to determine when it's increasing, we want to know when that's greater than 0. Or when it's decreasing, we want to know when that's less than 0. And so how do you find that out? Well, generally, you find when it equals to 0 first, and then you look on either side of all the times that it is 0 to see if it's positive or negative. Because think about how it's going to be positive, it's going to be increasing, but then it's going to flatten out and be 0 for a second, and then it's going to go back negative and be decreasing. So that's where we want to look at. We want it everywhere that it is 0 to see, because that's where it could switch from positive to negative. So let's look. So that's what we'll say is when is this equal to 0, and we'll solve this equation. So to solve this, you got to factor. So you factor out of 3x, you get x minus 1. And so we get that x equals 0 and x equals 1. So those are the values we want to look at. Those were the values where it equals 0, where the derivative equals 0. And so then if we look in between them, we just want to know where it's positive or negative. So let's think about a number bigger than 1 first. So 2. So let's plug in 2. And so we're going to plug in 2 into the derivative equation because we want to know at 2 is the derivative positive or negative. And so we should see if we plug in 2, what do we get? 12 minus 6. So that's positive. We don't care what the number is. We just want to know if it's positive or negative. And so we found that at 2, it's positive. And that means that entire section has to be positive, right? Because if it ever ended up being negative somewhere in that section, it would have to cross 0. It would have to be 0 in between. And it's not. It's only 0 at here. That's where it crosses. One way... Well, yeah, you can draw it like this. You can say here, the slope is positive. The slope is increasing. Here, the slope is flat. It's it's getting ready to turn around. Now, it doesn't have to continue. It doesn't have to be decreasing here. It's totally possible that it flattens out, but then just continues increasing. But let's see. So let's plug in a number in between 0 and 1. So if we plug in 1/2, is it going to be positive or negative? Well, look how it's easier to see if you plug it in this version, because 3 times 1/2, that's positive. 1/2 minus 1, that's negative. So we're getting a negative times a positive. So that is negative there. So there, the graph is decreasing. So here the graph is, decreasing. Right at 1, it flattens out. Here the graph is increasing. Now what about to the left of 0? So let's plug in like any negative number, like -1. And what happens? Well, 3 times -1 is -3. -1 minus 1 is -2. So we have a negative times a negative. So that's positive again. So over here, the slope is positive. It is increasing. So that's sort of what this graph looks like. It's increasing, and we can even write that down, because that's what they ask. It's increasing all the way this way, all the way from -infinity to 0. It's increasing. But then it's decreasing in between 0 and 1. But then it's increasing again from 1 up to positive infinity. And we know it never crosses back down to be decreasing again, because we found all of the places that it crosses, because it can only go from increasing to decreasing if the derivative is 0. Or undefined, but the derivative is always defined here. And so that's like the gist of these. You're looking at where is the derivative 0. If it's ever undefined, you're looking at where is it undefined. And then you're checking in between all of those values to see if in between those values, is it positive or negative. Because if it's negative at any point in between one of those two values, it's negative the entire way. Same with being positive, of course. That's what we did here. We found our 3 sections, the middle section, the left section, and the right section, and we plugged in a number from each section and saw what it was there, because that applied to the entire thing. All right, let's go to the next one. So the next one is a similar idea. We're looking for relative extrema. So what they mean by that is like a maximum or a minimum. And so just think, really, just similar to what we just did. Like, that's a maximum, right? And look how it's from when, well, look how for 1, that's when the slope is 0. Slope of the tangent line is 0. And it's when the graph is going from increasing to decreasing. And same with the minimum. A minimum is going from decreasing to increasing. Now, I don't like to try to remember the whole going from decreasing to increasing is a minimum thing. I like to think about it every time. But it's important to see that, so you can think about it every time. So what are we going to do? Well, we're going to find all of these points, and then we're going to test them. We're going to see where it's increasing and decreasing to see if those points are going to be minimums or maximums. So we're going to start the same way we did last time. We're going to take the derivative. So f prime of x is -1/2 minus cosine of x. And we want to know, when is that equal to 0? So we're trying to say, when is cosine of x equal to -1/2? So then you have to think about it. You have to say that cosine is 1/2 at pi/3. But then this is negative, so all students, so quadrant 2 and 3. So we want pi/3, but in quadrants 2 and 3. So that's x equals 2 pi/3 and 4 pi/3. No. Oh, yeah. Yeah. 2 pi/3 and 4 pi/3. So we're going to do our number line, and that's where we're going to look. We only start here carrying at 0. Oh my gosh, did my pencil just die? That's crazy. Hang on. Alright, we're back. So we get our number line. So 2 pi/3, 0, 4 pi/3, and 2 pi. And we just got to plug in values in between all of them. So probably easiest to plug in is like pi/2, pi, and 3 pi/2. And again, into the derivative, because we're not trying to see if the function is positive or negative. We're trying to see if the derivative is positive or negative. So let's do that. We plug in pi over 2 into the derivative. So what's the cosine of pi over 2 is 0. So that's negative 1/2 minus 0. So that's negative. You plug in pi. The cosine of pi is negative 1. So this is negative 1/2 minus negative 1, so plus 1. So negative 1/2 plus 1 is positive. And 3 pi over 2, again, cosine is 0. So it's negative 1/2 minus 0, so that's negative again. And that's all we cared about. So then we can even sketch out the graph here and say, like, all right, so here it's decreasing, here it's increasing, and here it's decreasing. And just when you do that, that allows you to see, like, where your mins are. So we definitely have a minimum at 2 pi over 3. And let's see, that's a min. And we have a max at 4 pi over 3. And now it's not totally clear exactly how they want the answer. They do kind of make it look like they want the point itself. So that's fine. We can find that. But then when we want the point, so realize again what we're thinking for. So like, this isn't a memorizing thing. This is like an understanding thing. That what did we like before? We wanted if it was increasing or decreasing at the values we plugged in. So that's why we plugged into the derivative. Now we want the value of the actual function at 2 pi over 3. So we got to plug into the original function. And so what do we do when I'll go ahead and I'll write it all out. What is f of 2 pi over 3? Well, it's 1/2 times x. So the 2's are canceling. So it's 1/2 times 2 pi over 3. The 2's cancel. It's just pi over 3. And then minus the sine of 2 pi over 3. So minus root 3 over 2. Okay, maybe we don't want that. Because then I would combine that into one fraction like that. And we're going to get a similar thing for the 4 pi over 3. So 2 of the things cancel. You just end up with 2 pi over 3. Minus, well then it'll become 4, I guess. 4 pi over 3. Because then we're going to get a common denominator to make 6. Because the other one, the sine in the third quadrant, all students take. So that's actually negative. So then we're actually subtracting the negative, so we're adding root 3. Okay. So the big important part was really the x values there. I don't even know if they wanted us to find the y values. But then, of course, if you have the x value, you can get the y value by just plugging it into the equation. All right, we're going to do the same here-ish. Find the relative extrema of that. Except for here, we have to remember the other thing we have to do is we've got to check and see when the derivative is undefined. It doesn't end up mattering that often, but you do have to do it. So we have to find when the derivative is equal to 0 and when the derivative is undefined. So of course, both of those, the first step is taking the derivative. So power rule here, 2/3, you go x squared minus 4 to the negative 1/3 times 2x. So let's clean that up a little. We'll have 4x. We'll have this 3 on the outside. And I'll go ahead and keep this as to the 1/3. Minus 4 to the 1/3. Okay. Okay, so that's the derivative. And we want to know when is that derivative equal to 0 and when is that derivative undefined. So first off, I would look at where it's undefined, because I would say what makes the fraction undefined. We also have a root. The root undefined you don't have to worry about so much, though, because that's just where the graph cuts off. But the divide by 0 undefined you do have to worry about. So where is this derivative undefined? When x squared minus 4 is equal to 0. So when x is positive or negative 2, the derivative is undefined. And so what does that mean? There's two kind of cases that could be. One, where there's a sharp corner, where there's an absolute value type of thing. But I feel like that I do think that's only going to arise when there's absolute value. The other thing that can happen, which is what happens here, is a vertical tangent line for a second. Because remember, back to like algebra 1, the slope of a vertical line is undefined. So that's where we're going to have to look at plus or minus 2. Not sure what's going to happen there. And then we have to look at when this equals 0. And remember, the whole trick about fractions is if they equal 0, you just multiply by the denominator, and you just get that the top has to be 0. So x has to be 0. So those are the points we have to look at. So then we should put that on a number line and say we've got 0, -2, and 2, and just check our numbers on all sides of those. And we're trying to see if it's increasing or decreasing. So we're plugging it into the derivative, which is this right here. And remember, we don't want the number, we just want the sign. So let's see. Let's start from the right. When we plug in a positive 3, is it positive or negative? Well, it's just all positive. It's just all positive. It's positive 12, and then you get 9 minus 4, which is positive. So it's just all positive. You plug in 1, on the other hand, see how on the bottom you get 1 minus 4. And the cube root of a negative is not a problem. It's just the cube root. It's just a negative number. So when you plug in 1, you're getting a positive divided by a negative, so you're getting a negative. However, when you plug in -1, you see the same thing happens on the bottom, so the bottom is still negative. But on the top is also negative. So when you plug in -1, you're getting a negative divided by a negative, so you're getting a positive. And then when you plug in -3, notice how the bottom just becomes all positive again, because -3 squared is a positive 9, minus 4 is positive 5, but the top is negative. So that's negative. Huh. So what does this graph even look like then? It makes me curious. So what is, I mean, from here it looks like a sort of sine wave thing is going on. I remember what this graph looks like. Let's take a look at this graph. So what do we want anyway before we even look at that? What are our relative extrema? So we have a relative min, and we'll just find the x values. We have a min at x equals -2 and +2, so plus or minus 2. And we have the max at x equals 0. Now let's take a gander at what this graph looks like. I remember this graph. Isn't that pretty neat though? Before we get off of that, let me just show this off for the YouTube video real quick. So the idea is you look at it in this orientation, it says Math Lab, but then you spin it around, no, not in that orientation, you spin it around in this orientation to here and it says Jordan. Just depends on which orientation you look at it in. That's pretty neat. Anyway, that's not what we're going for right now. What we're going for right now is to graph this equation. X squared minus 4 raised to the 2/3. So isn't that interesting? Because I said that we'd only have sharp corners in absolute value, but we have sharp corners right there. And you see the reasoning is because of this squared thing up here. The squared, when you square something, it kind of acts like an absolute value. You see, before it acted like that, but when you squared it, all the negative stuff becomes positive. So that makes sense. That makes sense. And you see that we are correct in saying what we said. And roughly, this picture that we drew is correct. Very roughly. Alright, so this next one we're doing the same thing. We got to find the relative extrema. So we got to take the derivative, see when it's 0, see when it's undefined. So now, how do you want to take the derivative of this? Do you want to use the quotient rule? Or I think you'd be having a little bit of a shortcut if you hearted it. So you could say that this is equal to x squared plus x to the -2, right? So now to take the derivative, you just have to use power rule. -2x to the -3. So 2x minus 2 over x cubed. If you wanted to go one fraction, then you'd have to go 2x to the fourth minus 2 over x cubed. And we want to know when that's 0 and when it's undefined. So if we're talking about relative extrema, we're not going to have a relative extrema where there's an asymptote, right? And we see that we have a vertical asymptote at x equals 0. But if we're ever looking for increasing or decreasing, it does matter. So let's go ahead and mark that we're going to have x equals 0 is where it's undefined. And I'm not sure why the textbook hasn't brought this up, but this is a little vocab word for those numbers. Those are called critical numbers, or critical values, I think more commonly. So the critical values are just where the derivative is equal to 0 or undefined. And so we found one, it's undefined at x equals 0. Now we need to say, when is this equal to 0? You know what? A muck gorilla did just ring a bell in my head. Although I don't think it was my physics teacher. I think it was my calc teacher. Called them critical points. But I'm pretty sure I've seen them called critical values as well. Alright, so we're not done with this though yet, right? Because now we gotta set the top equal to 0. So if we set the top equal to 0 here, why the top equal to 0? Because we set the whole thing equal to 0, and then we multiply by x cubed. So we're gonna say 2x to the fourth minus 2 equals 0. I mean, there's a few things we could do. I would just add the 2 divided by 2, so you get x to the fourth equals 1, and then you to the fourth root both sides. And we don't care about the imaginary, but we do still need the plus or minus 1 here. So now we have our critical points, or our critical values. And so we're going to put it on a number line to see when it's increasing, when it's decreasing. And that'll help tell us our mins and maxes. So let's see. And we're plugging it into the derivative, right? Because we just want to know if the derivative is increasing or decreasing. Alright, so let's start. I think I'm actually going to rewrite the derivative as 2x to the fourth minus 1 over x cubed. Because that'll make it easier to stuff like when we plug in something like 1/2 in between 0 and 1. 1/2 to the fourth just gets smaller. So 1/2 to the fourth minus 1 is definitely negative over a positive cubed. So this is definitely decreasing here. But then when it's bigger than 1, like 2, then the top is definitely positive. It's 2 to the fourth minus 1 is definitely positive. So that's definitely increasing there. And then what about on the other side of 0? What about on the other side of 0? Where we plug in negative 1/2. So when we plug in negative 1/2, when we plug it in on the top, what's going to happen? So negative 1/2 to the fourth, 1 over 16, minus 1, definitely negative. So it's negative on top, just like when we plugged in positive 1/2. But now it's negative on the bottom. So here we're getting a negative divided by a negative, which is a positive. And then when we plug in a negative 2, what do we get? We get a positive on top, and then on bottom is a negative cubed. So that's negative again. So what does this look like? So we're looking at decreasing, increasing, decreasing, increasing. So it looks like this might be a max. But then, honestly, you've got to go back and you've got to remember that's not a max. That's an asymptote, because x can't even equal 0. So you can't have a relative max at a point. So that's not going to count for a relative extrema. The only extrema we're going to have are these relative minimums here at negative 1 and 1. At x equals negative 1 and 1. And let's see. Let's take a look at that graph. Because that's just a rational function, right? Like, the reason you see this is because what's happening is it's going up and up and up and like that to an asymptote. Like, this is basically what the graph is going to look like. Two sort of parabola-looking things. They might go up, they might go down. Guess we didn't think about that. Yeah, they're both going to go up. Yeah, very much two parabola sort of looking things. Yeah. Beautiful. So that's what it's all about. You find when the derivative is 0, find when it's undefined, and then don't just blindly trudge on and say that this is a relative maximum. Realize that that is an asymptote first. All right, now we got our last problem. Okay, so let's put a little word problem to it. So, neglecting air resistance, the path of a projectile that is propelled at angle theta is y equals, that whole equation. Where y is the height, x is the horizontal distance, g is the acceleration due to gravity. Yeah. Let g equal that, v naught equal that, h equal that. What value of theta will produce a maximum horizontal distance? Oh, that's fun. So let's think about that in terms of what we've been doing. So we want the equation equal to what we're trying to maximize. Because we've been trying to maximize the functions. So we're trying to maximize the horizontal distance. Is that what y is? No. Y is the height. H is the horizontal distance. But that's what we want to maximize for. So is it going to be best to solve for that? Because when we tried to maximize the function, we wanted it solved for the function. So I think we'd be best off here. We solve it for h. So we go h equals y minus all of that. But surely they don't want us to take the derivative of that. That's nutty. Yeah, I feel like I'm definitely making this too hard. Let me clear out my brain. Let me rethink what's going on here. So, what value of theta will produce a maximum horizontal distance? I mean, obviously, we all know the answer, right? I think I should solve for x. All right, hang on. We got to think about this. All right, so I went back to thinking about it, and I realized the horizontal distance is not h. I literally underlined it. That is the height. We are not trying to maximize the height. We are trying to maximize the horizontal distance, which means, like we said, we don't need to solve for h. We need to solve for x, which is much harder. But we can still do that because this is a quadratic, right? X squared, x, constant. So we just have to use the quadratic formula. So what do we have? We have negative tan. So negative b plus or minus the square root of b squared, so tan squared, minus 4ac, so 4 times g times secant squared of theta over 2v naught squared, and then times c times h, all over 2a. That's what we get when we solve for x. But it equals y. It doesn't equal 0. Oh my gosh, I can't believe I'm having so much trouble with this problem. So to get it to be 0, I'd have to subtract y from both sides. So then my c would be like y, so this would be like h minus y here. What did they do? Okay, well, they plugged in the numbers first. That was intelligent. That was definitely intelligent. So we just wanted to find the equation for the distance traveled. Oh my gosh. To find the distance the projectile travels, let y equal 0 and use the quadratic formula to solve for x. Let y equal 0. And you want to let y equal 0 because that's where it's going to hit the ground again. So then x is just the distance. And then they plug everything in because that's more intelligent. Y can be 0, but it's arbitrary anyway. Oh, I thought the maximum result would be 45 degrees. So what is it exactly that they're saying to do? They're saying we've got to write an equation for the distance that this thing goes. So it's like, so that's like we definitely want to solve for x. Oh, if it's not flat. Okay. Yeah, so I mean, I get the time of impact y is 0. And so that's just going to get us the distance traveled. Okay, so the distance traveled until it hits the ground. Yeah, okay. So we want to know when it hits the ground. We want to know the x value that it hits the ground again. So, oh yeah, it's also starting up in the air. So we want to know the x value that it hits the ground. So that's why we say that y equals 0. So then we can use the quadratic formula. Except for this is just a plain h because we just said that y is equal to 0. And then we need to plug in all of the stuff that we know. Might have been easier to do that earlier, but we can still just do it now. Probably. So we'll go negative tan of theta. And then it's plus or minus, but the minus version is going to be like from before it was launched. So we definitely want the one after it's launched. So we're going to go with the plus one. And then I'm just going to plug in for now. Tan squared of theta minus 4 times 32. So that's 128. But then it's negative, so that's plus 128. Secant squared of h. No, secant squared times h. So secant squared times 9. Divided by 2 times v naught squared. 8 times 8 times 9. And all of that divided by 2a. Oh, holy moly. 2 times all of that. So I guess those 2's cancel. So you end up with negative 32 secant squared of theta over 2. I canceled out the 2. So times 24 squared. That's brutal. Except what is nice, was very nice actually, is all of those cancel out. And so you're just left with tan squared plus secant squared. So, because what is that? Tan squared plus 1 equals secant squared. So does that just not come out nice? I mean, that should have been minus. So no, that seems all correct right now. Really, tan squared plus secant squared. So I'll assume I'll do the assume it was launched from the ground thing after I hopefully end up finishing this out. So this cancels with this and just leaves an 18 on the bottom. And what's tangent divided by secant? Sine. So I get sine over secant squared. Is that just sine times cosine? Because that's sine over cosine divided by, so times, well, it's divided by 1 over cosine. So it's times cosine squared. So yeah, that's sine cosine. And this was just tan squared plus secant squared over what the heck? The plus or minus went away because we were ignoring the minus because we only wanted the plus 1 to the right of where it's launched. So yeah, that's what they got. And then they just look at the graph. And then they just look at the graph to find the maximum angle. Oh my gosh, what cheats. So then they just go like, okay, we're just going to look at this on Desmos. So what even is this? This is x equals this. And then so we find the theta that gives us the biggest x value. I guess we'll go ahead and play their games. Minus sine of x, cosine of x, plus. I feel like I might have messed up the math somewhere. And if I mess up the math somewhere, I'm like prepared to just leave it. So I don't actually want that. I just want this one divided by secant squared. Then they want the angle that maximizes it. They're giving me 2.849. Wow. So we just solved for x wrong. That was crazy. You want the zeros of the function since the function will be periodic? You want the zeros. We weren't looking for the zeros though. We wanted to maximize that function. Because we never even took the derivative of it. So yeah, the zeros are just like at 90. Because that's when it's like going straight up and down. I just somehow messed up the simplifying of this equation. I know I'm good with that. I don't know. I don't exactly see how they manipulated that. Oh, did I not do the 18? I didn't do the 18. There needs to be 18 out here. Do I actually want the minus? The negative one? No. What? There we go. The negative canceled. Right, and I said the negative... Well, no, did I not say the negative canceled? Oh gosh. I would just get this one removed wrong and move on. It's a beast. I thought we took the derivative. No, we never took the derivative. I just don't see how that negative canceled out. And I'd like to see that. Yeah, from a pure test-taking strategy, it's definitely important to just leave. But I'm trying to get all of these, or at least understand why I'm not getting it. Because the G is the negative. The G is negative. G is negative. So that's why it's divided by a negative. Oh, so it's a negative divided by a negative. Yeah, so that's the negative, and that cancels out. Okay. Yeah. I see that. Okay. Let me give a full explanation of this from the top. So what are we trying to do here? They give us this equation. They give us this equation. And we want to maximize the horizontal distance. We want to maximize the distance it's going to travel. So the first thing we want to do is we want to write an equation for the distance it's going to travel. So if we think about, well, it's going to hit the ground at y equals 0. So if we make y equal to 0, that'll show us the horizontal distance that it's traveled. So that gives us this equation. But then the idea is we're trying to maximize x. So think about all of the other things that we've done where we try to maximize the function. Well, it has to equal, because normally we're trying to maximize the y value, but it's y equals. So all that to say, we need to make this x equals. We need to solve for x. And the only way you're going to solve for x here is with the quadratic formula. So you just got to run it. You just got to go negative tan of theta. And then we'd say plus or minus, but you think about how there's going to be one answer to the left of where we're shooting it from and one answer to the right of where we're shooting it from. And we want the one to the right because that's like positive time. So we want the plus version. So negative tan of theta plus the square root of b squared, so tan squared of theta, minus 4ac. 4g secant squared of theta over 2 v naught squared times c times h all over 2 times this entire fraction. And then frankly, we kind of just did more work than we really needed to do. Because now, I would just say we're going to plug in our numbers. And we're going to have to go to the calculator anyway. So, we just plug in our numbers that they give us. Go to the graph, not that calculator, but this calculator. And we just type it in and we say, oh look, here's the graph. And we can just see the maximum. The maximum is right there at 35.26. That's all they wanted us to do here. But honestly, there's not really a better way to do that if we can use the calculator. You still, as far as I can tell, need to go through all of that work. But that's harder than most problems we're going to have to do.